Well, good afternoon. Thank you for coming to today's physics colloquium. Our speaker today is Baylor Fox-Kemper. Here he is. He's a professor of the Department of Earth, Environmental, and Planetary Sciences at Brown University. Baylor received his PhD from MIT, dividing his time between the Green Building in Cambridge and then Woods Hole Oceanographic Institution down in Woods Hole. After that, Baylor took several positions, including one at NOAA, before he came here as an assistant professor in ATOC. And so I think quite a few of you in this room know Baylor, friends of Baylor. So it's a sort of a homecoming of sorts. Today Baylor will be talking to us about waves affect and detect climate. So please join me and welcome Baylor to Boulder.
Thanks, everyone. Oh, yes, it is on. Thanks, everyone. Thanks for coming, and hopefully this will be somewhat entertaining or educational, something like that. Let me see if I can make this slightly darker. This one.
Yeah,
there we go. Because I didn't choose colors that are quite bright enough to work at full lights. Keith, Julie, and I were just talking about this a second ago. How did we get interested in the idea of whether waves affect climate or not? One is just because waves are nice. You can go to beach places and just like enjoy the waves. And so you'll notice a lot of the backgrounds I've chosen are just beautiful beachy places, which is a nice thing to think about, especially this time of year. And then the other thing is that it was sort of an unexplored dimension. A few pieces of the theory had been laid out in a couple of different places, and certainly, the dynamics of waves on their own had been thought about for centuries, and so had the climate system. But it took a while to kind of get a bigger picture how those pieces fit together. And then the other thing, which is worth mentioning, and I'll come back to this at the end, is I had a grad student who worked with me here, Sean Haney, and he got his PhD from CU in 2015. He actually tragically passed away 2 years ago, and so I'm actually on my way to give a memorial talk in his honor at Scripps, which is Institution of Oceanography, which is where he went after CU. And so on that note, since Sean thought a lot about waves and some of the process interactions between waves and other things, I thought it would be nice to talk a little bit about him and kind of in this context, but also I'll be talking about that next week at Scripps. So that's how we got to this piece of topic. And so there are 3 different hunks of information. They've also got sub-hunks of information underneath them. These sub-hunks may not make any sense to you at all, but I would hope that at least the 3 big bullets, waves affects ocean mixing and currents, that maybe is what you're expecting to hear about. If waves break, they certainly do mixing. We're going to talk about a slightly different kind of mixing that they interact with. And then a somewhat surprising result, in particular, that on even a larger scale, waves can interact with currents. Waves detect climate change, and this is where we're starting to get into what we mean by climate, and you'll see how that comes around. That has to do with how waves are detected, but also how winds and transfers between the atmosphere and ocean are detected. And then the last piece is waves affect the mixed layer, and thus climate. And so it's a little bit about how we model the mixed layer, or how we conceptualize modeling the mixed layer. And so Klaus Hasselmann, who won the Nobel Prize in Physics, together with Suki Manabe a couple of years ago, had thought a lot about this problem. And so we can bring these pieces back together in the end and get a kind of holistic connection between them if we take advantage of the kind of model that Klaus proposed. So let's be clear about what I mean by a wave and a current and a front. So waves, I'm talking to a physics department. We all know what a wave is, but an important aspect of waves is that it goes from one place to another without moving the medium that it's traveling through. That's maybe the most critical aspect of a wave. It is different from a current because a current is kind of similar. It has a velocity, but it does move the stuff from place to place. So that's a distinction between a wave and a current. And then the other thing that's going to come up a lot in the talk is a front, which is really a sharp change in properties. And on a rotating planet, a sharp change in a property like density or salinity or temperature is often associated with a current going in the other direction. So if you have a jump in density, you tend to have a current going along it. So the wave isn't the medium. This is one of, I don't even know if this is an apocryphal quote or a real one, but it's a funny one. And it also reminds you that the wave doesn't move the cat in order to make the signal go, or the cat without the cat. Okay, so with that introduction, what are examples of waves? So surface water waves, waves of the beach, these kind of waves, which I'll come back to, they're a little different from the waves of the beach. Many of the processes leading to El Nino are actually waves. They are topological waves in the sense of condensed matter, thinking about topology, which is interesting, a topic for questions or discussion afterwards possibly. Sound is, of course, a wave. Phone calls are a wave, a different kind of wave that's both sound and other things in between. Radio, but also epilepsy, traffic jams, the aurora borealis, and someone who is an expert in nonlinear dynamics told me that he was really interested in building a wave that was a ring of toilets, that when you flushed one, it would dump into the next toilet, and it would just go around in a perpetual motion of flushing toilets. That would have also been a wave. But anyway, we're going to focus on open ocean surface gravity waves. So one thing you might notice, so this is the ship at sea, and I think this is taken from the Flip platform, which is a floating barge that was semi-stationary when it was in the waves, built to observe waves largely. The waves aren't breaking as much as they are at the beach. As waves move into shallow water, they actually slow down, get taller, and then tend to break. So they are steeper and more likely to break in shallow water than they are out in the open ocean. We're actually going to, the theory we're going to move through assumes a limited wave steepness. So we wouldn't want to be in the surf zone. We want to be farther out than that for that reason. Okay, so on to topic number one. So here is either a fantastic picture or a terrible picture, talking about climate change, but also environmental issues. You frequently have ones that are both. This orange stuff is oil after the Deepwater Horizon disaster. And here's an airplane for scale. And you can see that it's clustering together. It's not, oil actually does turn this color of orange after it's been in the sun for a while. This is taken from a satellite, actually, so it's really a high picture. And you can see that the clusters, the lines of them are perpendicular to the wave crest that you can see glinting in the sunlight here. That's a characteristic feature of something called Langmuir turbulence, that there are windrows that form of debris at the ocean surface in a direction that's perpendicular to the wave crest and the wind. These are some details for folks who are on the GFD side of things. Most of them are not important, except some that I'll touch on again later. So one of the things that waves provide is Stokes drift. And Stokes drift is not the orbital velocity that a surface wave has, but it's a residual if you average over multiple wave periods, because the orbital velocity would actually orbit in a circle, but if you follow the motion of a particle in a Lagrangian sense, every time you come by, you're going faster at the top of the circle than at the bottom, because there's a decay scale for the orbital velocity. So in a finite trajectory integral, you get a little drift, and so there's a Stokes drift, is what that extra drift component is called. There are particles that you can see in this little video. It is a part of the transport of particles, even though the wave orbital velocity doesn't move particles anywhere the Stokes drift does on net. And it tends to be stronger at the surface and weaker at depth. So there's a shear to that velocity field. This is a nice monochromatic wave that we're looking at that has kind of one dominant period. But actually in the real world out there, if you went and did a Fourier transform, a directional Fourier transform, so this is a polar plot, you might get something more like this. You get a big cluster with a lot of energy that's coming from the direction of the wind, where the waves have a big, kind of broadband spectrum around them. But then you might also see some swell coming from other places going in different directions. So swell is a non-local kind of wave that was formed by wind far away and then propagates. And you might see all three superimposed at a time Yeah.
Is this what I should be thinking of to understand the previous image of these streaks?
Not quite. It's part of the story, but we're going to have a little bit different mechanism. The streaks are not collecting because of the Stokes drift collecting. It's one more step more complicated, but we'll get there. But you could also calculate the Stokes drift just as well for even a complicated wave spectrum. It's just a little bit more difficult thing, and it's not unidirectional the way this one is.
Question.
Yeah.
Does the Stokes drift mean that there is a current and a wave
Sort of. You also could have a current imposed on top of this. The waves could be propagating through a current. And no, the Stokes drift we think of as part of the wave, but it does have a time average over the wave phase. And so what we're going to talk about on the next slide is that it's important in the asymptotics linking the interaction between slow things and fast things.
If there's an impurity in this water, is it moving to the right, or is that not how I should be doing?
No, it is. And if you track one of these little particles, you can see it actually is also moving kind of with the Stokes drift. So the transport of material goes with the current plus the Stokes drift on average, even though in a wave it's actually going kind of back and forth. And that might be the biggest velocity that something experiences. That doesn't lead to a net drift. Things like the Coriolis force also go with the Stokes drift. There is a Stokes Coriolis force because that net drift there is also moving along with the planet, and so you get a combined force like that as well.
Isn't there mass transport of those particles?
There is a mass transport of the particles, and under the Stokes drift, and it's not.
Tracking that from when you
Yes, if you want to call it a current, because I told you a current was anything that has a motion of the medium, sure.
I'm just following up.
That's true. That's good. No, that's good. If you want to keep it that way. But now I want to talk about a slightly different thing, which is to say, what if we try and break this down into different asymptotic scalings and think about how they link to each other, and maybe we can put them together into some kind of theory. So waves are kind of small. This wavelength isn't that long, just a few meters. So on a climate scale, it's very small. They're fast. They have a period of maybe 5 to 10 seconds for that swell wave I was talking about. There could be some bigger things that are large and also fast, different kinds of waves. But then most of these currents, also things like the Stokes drift, are on this kind of larger, slower evolving scale. You know, the Stokes drift is a wave average, but other currents would also be in large and slow. So suppose we take a system and break it down like this. We could simplify unit 1 and unit 2. Suppose we just say, well, let's just pretend that they're waves and nothing else for those scales. We could average over them, and we would get the Stokes drift from deep water waves, which is something you can know analytically. And it turns out that that Stokes drift then couples in this large, slow dynamics in a special way. So if we have a large, slow, kind of turbulent evolving flow on the kind of much longer than a wave period scale, maybe 20 minutes to an hour kind of time scale on something that's maybe hundreds of meters rather than the wavelength, which might be tens of meters, that would couple strongly with the Stokes drift because the Stokes drift has this persistent nature to it. So it turns out if you do this, you get something called the wave averaged equations, or sometimes the Craig-Leibovich equations. And it basically looks like 1 and 2 hooked to 3 coupling terms we know about. And the only thing they see of the waves is the Stokes drift. Because they are large and slow, they are so slow that they don't notice the wave orbital motion, but they do notice this persistent effect from the Stokes drift. So here, so this large slow, we're neglecting the small slow. There's not a lot of small slow, probably. It's an idealization here that we can take the small fast and the large and fast off as waves. We could try and do a direct simulation of all these scales at once. That's not computationally possible. What we can do, or it's just barely in kind of to do some of this, what we are going to do is we're going to see simulations of the large slow with an imposed wave field and think about how the waves are driving large slow stuff. So here's the classic example of this. As I said there, they use the windrows underneath. So here are some little fronts that might be just kind of randomly at the surface. And they're going in the direction of the wind, and the waves are going together. And so suppose that just happened to be there. Now, this anomaly has an anomaly in vorticity. It's rotating this way on one side and the other way on the other side. And that Stokes drift from the waves coming this way would tend to tilt that vorticity down into the horizontal because it's moving faster at the top and the side. So the vorticity tilting term would tend to rotate it down. And you would start to see vorticity in this orientation as the result of that tilting. So the vorticity starts off in the vertical, going down and up, and then it gets tilted over into this direction, and that generates a kind of cellular turbulence like this that's overturning, called Langmuir turbulence. And now, looking at these cells, what do? Well, they converge at the surface here, and then they diverge at the surface there. So if you put something buoyant that couldn't follow them as they go down, it would just accumulate here at the convergence zone, and it would get depleted from the divergence region. And so you would pile up along these streaky lines windrows of buoyant material. So I claim that that's what's going on with that oil, is that it's actually an example of Langmuir turbulence, which is there because of a combination of kind of velocity variations and vorticity variations and the random kind of turbulent motions that are hanging up on the surface together with this Stokes drift that's tilting it over and intensifying it in the horizontal. So it's not the Stokes drift itself that's doing the windrow formation. The Stokes drift is tilting the vorticity, and then that vorticity is doing the windrow formation. So this is the mechanism called Craigley-Rivich 2 or something, but that's a classic mechanism. And now here is a handful of those simulations I was saying. So we're just simulating large, slow turbulence. And up here we have wind only blowing at the surface, and here we have wind and waves. We have a kind of simple density profile, so we have a well-mixed layer at the top and then a stratified layer below, so not everything doesn't penetrate to the bottom of the box. There's a density anomaly that's preventing it from digging down to the bottom. But you can see that these two are qualitatively different. There is maybe stronger flow down here, at least at the beginning, and then this has an oscillation which makes it. But you can also see that the streaks that are happening are slightly different oriented. They go in different directions between the two. And those subtleties are the kinds of things that we see. So Langmuir turbulence tends to be stronger. It has another source of energy. Effectively, it can extract energy not only from the wind, but also from the waves. Maybe the waves were formed by wind earlier, so it's still wind energy ultimately, but in that process level, it has two different energy sources. And there's a little bit about not only the strength, but the direction is different. On small enough scales, at the bottom of the scale cascade here, both of these kinds of turbulence become three-dimensional kind of Kolmogorov forward cascade turbulence. But on the largest scales, their anisotropy is detectably different in the real world and in experiments and in models. Does that make sense to everybody? So suppose we want to put this extra little bit of mixing that comes in from the Langmuir effect into a climate model. We need to handle a bunch of different things. We'd like to know what direction those windrows are oriented, for a reason I'll talk about in a second. Maybe we've seen on that typical wave spectrum that the waves might not be going in the same direction as the wind, so we might need to handle that somehow. And then there's also a Coriolis-related shear that's different between the Langmuir layer and the wind layer. And so we basically did a bunch of simulations of this in a lot of different conditions. And I'll go forwards and backwards, with the wave direction changing and the wind direction staying fixed. And then we had a bunch of different theories, each represented by one of these arrows. And only one of the theories actually does a good job of predicting the blue line direction here. And the blue lines, this is vertical velocity, so that's the convergence and downward motion. That would be where the windrows would form if we released particles in this flow. And you can see that the green line does a decent job. So, okay, that's one thing we needed to know. We're prescribing the wind and the waves, and so what we actually do is we anticipate the direction of that shear that tilts the vorticity down. So we need to know the orientation of the Lagrangian shear, so the shear including the Stokes drift part and any mean currents that might be driven by the wind together without solving for the Langmuir piece itself. So there's a turbulence parameterization involved that kind of gives us what the vertical mixing is like, and there's a wind-driven current part of it.
But the waves are going this way.
The waves are going this way, which is like the waves are going a little bit above each of the arrows, and the wind is going a little bit more horizontally. So one of the arrows is actually just in the wave direction. I think it's this light green one. The dark green one does a better job. It's somewhere in between. And so the somewhere in between, the reason why somewhere in between is good is because now in that orientation, maybe it's just the component of the wind and the component of the Stokes drift in that direction that leads to the turbulence energization. At least that was our hypothesis. And that actually does a pretty decent job. So this is a bunch of vertical velocity squared, so basically kinetic energy profiles that come out from a different wave and wind conditions. And this is what happens if we, rather than taking them in different directions, we first project them into that predicted direction and then ask, what do they do? You can make them collapse on each other. So this is a simplification of that more complicated problem by just orienting our whole forcing direction into the directionality that we anticipate those Langmuir cells to form. And when we do that, we get some kind of funny projection operators. But this is enough to now go into a climate model. If we have a scaling for the vertical velocity squared, we can convert that into vertical mixing, and we can just put it into a climate model and ask whether it does anything if we have a scaling for the vertical mixing. I'm going to come back to that in a minute. But what about waves affecting bigger things? Like those so we had waves, they maybe have a 10-meter length scale, and then we had those Langmuir cells, and they're maybe 100 meters, a couple of airplanes across. What about things that are maybe kilometers across? Do the waves interact with those things appreciably? So things that are a kilometer across can refract and reflect waves. That's one way that there is an interaction. That it was known for a long time. But we were wondering whether there was like that same tilting mechanism for the Langmuir cells, is there something else like this kind of similar to that happens on currents? And when we did some rough scaling, it turns out that maybe there might be. But let me tell you what some of the things on larger scales are. So we said they're fronts. So here are some examples of fronts. This is temperature on this side. This is false color. So you can think of this as like biology and things that are making water properties different from place to place. But you can see there are these long streaky features that are fronts and water properties. And there are typically currents along these and maybe eddies that are mixing them up as well. So where does all this stuff come from? Well, it comes from hydrodynamic instability of a rapidly rotating planet. And so this down here, this little movie, which is not repeating for me, but I will start it again, is just a simulation of exactly that. I have warm water on one side and cold water on the other side. It forms a current along the front between them, and then that current goes unstable to these kind of rolling up eddies. This class of hydrodynamic instability is called baroclinic instability. It's one of the ones that we want to talk about. And you can see those eddies are maybe a couple kilometers in size when we have realistic figures. So this is another scale up from the Langmuir cells. And in a recent paper, we actually went and tried to figure out how big that mixed layer instability scale is in the real world, all over the world. And it ranges from about a couple kilometers near the poles or in the summertime to maybe 10 kilometers in the wintertime near the equator. So that's a solved problem of a sort, how big they are. There's a smaller instability, about 25 times smaller, called symmetric instability, which will play a role later that I just wanted to show. Also has a complicated pattern in the real world. This looks a little different than the other one, but it forms at fronts in the same way. So in collaboration with Keith and Peter Hamilton, who's now here in mechanical engineering, we set up a bunch of simulations to try and do both of these at the same time. So we made a really big domain, and then we basically did those Langmuir calculations inside a really big domain. So the first calculation I showed you was maybe 200 meters by 200 meters. This is 20 kilometers by 20 kilometers. So it's 100 times bigger in both directions. So it's a whole lot bigger calculation. And you can see that some little Langmuir cell kind of things kind of happen in different places, but then there are also these temperature fronts, and then there are these eddies. And so we thought we were going to see an interaction between these little Langmuir cells and maybe the fronts, or Langmuir cells and the eddies. And we did. It wasn't very strong in this particular setup, but that was one thing we were examining. Let me zoom into one of those. And this is what it looks like. So these colors here are showing you temperature, so that's really the front. And where I've colored, or where Peter actually has colored, is on the regions of large vertical velocity. So it's basically showing you the temperature of the windrow regions where they're going down. But you can see that there's a front and a current along the front flowing through the middle of these Langmuir cells. And so, and we were thinking that there was a strong interaction there. That was one thing that we tried to scale out, but something funny also happened. So here's one of those fronts in temperature, just shown in a little box for visualization from the side in a second. And notice that that front is going the same direction as the wind and the waves. And if we look at the vertical velocity, which is kind of just a stationary picture of that movie we just saw, you can see there's a really large vertical velocity, downward vertical velocity, right on top of that same temperature gradient. So if you were to release a bunch of buoyant things, there would be little windrows everywhere, but there's kind of a super windrow sitting right along that front. And that's because there's a separate circulation, not just a current along the front, but an overturning circulation that's concentrating that front into itself. That's a process called frontogenesis. And in rapidly rotating fluids, that's something that happens. When you get a front, it tends to sharpen itself and make itself stronger under lots of conditions. Here's an extreme example. Keep your eye on the pink drifters. Each of these is like a little drifter with a ring at the top and a little sail and a GPS tracker. And this is a release in the Gulf of Mexico near that Deepwater Horizon spill. And you might be very confused why they end up at a point. The video is not running backwards in time. They actually did start out. They were spread. This video is a little later than that, but they were initially spread out over about 10 kilometers. And they reached within 100 meters of each other because there is a convergence into a frontal feature that's wrapping up on itself, that's drawing all the stuff in. So just like that front was kind of drawing things in the drifters in the simulation, this is it happening in the real world. And you're imagining kind of a circulation like this. There's light stuff and heavy stuff. The heavy stuff goes into the front. Oops. I may have just lost my, oops, well, all right, my battery died. But anyway, so the heavy stuff goes into the front and then goes down, but anything buoyant would get left behind right along that front. And maybe we should have known this, because if you go to places where there's sea ice, you can see eddies and fronts very clearly in the sea ice, which means that it was already converging. Like that mushy sea ice was just getting brought into these kind of features. So it turns out that this whole class of little eddies that do this like to do this overturning. They do this convergence. They also tend to tip over as the eddies form. And so they're another part of understanding how this boundary layer is getting mixed. And the reason why waves have something to do with it is that if you go into that overturning, so let me do it like this. If you go into that overturning that I was talking about, so here's the warm stuff coming up, here's the cold stuff coming up, and then together they go down. Here is the overturning, the pattern of overturning that it does. There's a little dip right there. And if you examine the forces on that little dip, one of them is actually the same tilting over force that works for Langmuir circulation. So even on this much larger scale, this front that's many hundreds of meters wide, the same coupling between the surface gravity wave, Stokes drift shear, and a current is pushing downward in kind of the same way. So that Langmuir mechanism also scales up to bigger scales. It's not as strong on bigger scales, but it's present. And so if we think of this as which kinds of things are resolved, whether we have a Reynolds number or a Rossby number on the grid scale. On those smaller scales, we had a much higher Rossby number, a much higher Reynolds number, different kind of regime. We're going to a regime now where things are much slower. They're feeling the rotation of the Earth much more. They're much bigger, but they are still feeling that downward force. And if you write out the vertical velocity equation, which is down here at the bottom, with, well, Einstein notation, commas for partial derivatives if you want, but primarily the dimensionless parameters scaling the different terms out front, this term right here is the culprit. That's the one that pushes the stuff down, either in a Langmuir cell or in that front. And it has a factor epsilon on the front, which is this scaling right here. It's the Stokes drift times the depth of the motion over the depth over which the Stokes drift varies, Coriolis parameter, and horizontal length scale. That thing is actually hard to estimate on its own, but it's pretty easy to estimate comparison to the Rossby number, which is that guy up there. Their ratio, a lot of the difficult factors cancel out, is pretty easy to calculate, and that's what the map above is. So for those of you who know a little bit about rotating fluids, the Rossby number we use to measure how important the rotation is versus inertia. When the Rossby number is large, inertia is really important. When the Rossby number is small, rotation is really important, and the flow kind of linearizes itself. People worry an awful lot about finite Rossby number dynamics in atmosphere and ocean dynamics. So they think like, if the Rossby number is 0.1, like it's importantly nonlinear. So in effect, this new force that people don't talk about very much is changing the balance whenever, more than the Rossby number effect, whenever that ratio is bigger than 1. And you can see all of those yellow and red colors are bigger than 1. Yeah, did you have a question?
Yeah, no, I missed this is just Navier-Stokes equation, but you wrote it for the transverse component and Z component?
So W is vertical velocity, V is horizontal velocity component. J is actually a component. It could be either, I'm separating out the vertical component from the horizontal because they have different scales.
But is VL prescribed, or there's not an equation for VL?
VL is the Eulerian velocity plus the Stokes drift.
Right. But is there an equation for VL?
There is an equation for VL, which I just didn't write, but it's a different one than this one. Right. It involves that Rossby number in an important way.
It does or doesn't?
It does. Yeah. So I'm just not showing you all the equations. They're not, whatever, they're 8 equations to close the set. And I can show you the whole set if you want. But the important term is that one there that is just basically a downward force.
The last one?
This one right here. It's experienced as a downward force, but it's really a wave average interaction with the current that's flowing along.
And what's VL versus VS?
VL is the Eulerian velocity, so a current, plus the Stokes drift, and Vs is just the Stokes drift. So it's a coupling term between the flow that's carrying stuff around, the Lagrangian flow, and just the Stokes drift part. So the waves are coupled and pushing downward sometimes in the vertical velocity equation. That makes sense?
Accelerating in the longitudinal direction.
It's accelerating, the time derivative here is on the vertical velocity. It's accelerating, it's pushing downward when they're aligned. So there's an Einstein sum on the JJ. So if they're going in the same direction, it's pushing downward. If they're going, yes. This is the buoyancy, so it's pushing the same way that like dense fluid sinks. This pushes down, but with that epsilon factor as the scale factor. Okay. So this is not a trivial effect. So it's something to think about. Okay. So what about the instabilities? So that's about the currents. What about those little eddies that we're forming? Are those affected by the wave interaction? So you can go back and re-examine the wave dynamics together with the instability properties of the different kinds of instabilities that form along fronts. There are lots of things that you might consider. This is an example of a hurricane wake. So it's like a mixed trench that's now restratifying, and you can see all kinds of different phenomena are going on all at the same time. So if we want to figure out how long it takes for like a mixing event to heal, we need to know all the rates for all the different processes that contribute. So it turns out that if you do that, the big eddies are not strongly affected by the interaction with the Stokes shift, but that symmetric instability, the ones that are 25 times smaller, is very strongly interacted. So this is what Sean's PhD thesis was about, and this is a simulation that Sean set up. And there is a sort of mystical quantity called potential vorticity, which is it's a combination of the vorticity and the density of the fluid. And the important thing is that it's materially conserved and it's forced at the surface by different kinds of conditions. So on the left, we're watching the potential vorticity evolve. And you can see there are negative regions and a positive region in the middle. And that just has to do with the fact that there are different currents coming in and out of the board with the little arrows in the board and out above. So we're simulating something that has two fronts going in different directions into the board. And then, this is where I need the pointer, you can see that in the part where the potential vorticity is positive, there's one kind of phenomena going on and it's not going very deep. And then here where the potential vorticity is negative, there's a clearly different kind of phenomenon and it's going quite deep. So it turns out this is Langmuir mixing, like we just talked about. And this is symmetric instability, which is enhanced by the Langmuir mixing mechanism. So even those larger phenomena are feeling the effect of the waves together. Oh, you're going to do batteries. Good. And then, so the surprising thing, when we got into this, we thought we were going to be doing Langmuir and then big things. And the Langmuir was going to talk to the big things, and the waves weren't going to talk to the big things. But instead, it turns out the waves also talk directly to the big things. So you have a lot of new interactions to think about. All of these phenomena exist in the upper ocean. And so they all have some effect on the upper ocean mix layer, how much mixing it gets. And so if there's extra mixing, it'll deepen. If there's less mixing, it won't deepen. And all of these effects, though some are bigger than and some are smaller, they are all too small to be directly simulated in a climate model. So all of this phenomena, if we want to think about it in the climate context, has to be parametrized with some kind of mixing scaling. So I'm not showing you how we come up with a mixing scaling, which is a long and complicated story. Oh, one more thing. This is just showing that depending on which way the waves are going, they can either stabilize or destabilize those symmetric instabilities that we saw on the flanks. And this is one example showing that this should be stable except for the presence of the waves, which makes it have these symmetric instabilities up at the top where the waves are. And this should be unstable everywhere, but the waves actually have made it more stable. So you're switching on and off the instabilities with the interaction with the waves in this case. So, all right. So we've got waves. We know they can affect mixing. Maybe a much wider set of mixing ideas than we would have had before because they're interacting with fronts. They're interacting with these larger submesoscale features. We figured out how to project them into one direction and then came up with a scaling for their strength of mixing. So we have the ingredients to come back and think about their impact on climate. But I want to talk about how waves detect climate change as well. This is an intermediate topic before we jump back to this last piece. Are there any more questions about part one before I jump to part two? Okay. So this is maybe the part that you might have thought. This also gives us a little introduction into some of the concepts from climate change. So this is the latest version of what's called the hockey stick figure. This shows surface temperature on this axis. And this is paleoclimate reconstructions since the year 1 up here to the year 1850 when industrialization started, and then here's 2020. And basically it looks like a hockey stick. It jumps up at the end. That is evidence that the Earth has been rapidly warming. This is all from observations or paleoclimate reconstructions. And if we go back in deeper time, this is actually the warmest multi-century period in more than 100,000 years. So it's a hockey stick a long way farther back in essence. The shaft of the hockey stick goes a long way back that way too. But this doesn't tell you anything about cause of why there's global warming. This side tells you about cause. And this is showing climate models that don't include humans down here in the green spread. So there's a few dozen climate models, and their average is this black line, this darker teal line. And then here in the tan colors is showing climate models that do include humans. And since sometime in maybe the 70s, they're separate from one another. So the climate models that include humans are systematically different from the climate models that don't include humans. And then the last wrinkle here is that this black line is the observed temperature record, the same as this one. And you see that the black line stays only inside the cluster that has the human impacts in it. So the Earth is warming, and it's warming, as far as we know, because of humans. There are other lines of evidence to sharpen this, but this is maybe the simplest way to understand it.
Can you give some idea of how you separate those two, like with and without?
Yeah, so this one has greenhouse gases and land use change and aerosols that come from soot, like from pollution. So this has basically changes to the land surface because of human development and changes to the atmospheric constituents because of human emissions.
You measure those things and take them out.
So they're measured, and they're measured and added into the models. So they're part of the way that the Earth responds to the sun's light in that case, and tries to readmit that energy back out to space. And then down here, you basically keep the same volcanoes, keep the same solar forcing, all the solar cycles and stuff, but you just don't add the greenhouse gases, you don't add the aerosols, you don't add the land use of developing cities. And so,
Bottom one is simulation only, obviously.
yeah.
But then
This,
one is simulation, and then which one is simulation, which is actual measure?
so the simulation spread of simulations is this, and the black line is the observations. So the observations only match with the ones that include the human effect. All right, well, the Earth is warming, surface temperature is warming. What else is warming? Well, actually, the oceans are absorbing most of the energy, and along with it, the oceans are expanding because of that. When the water gets warmer, it gets bigger, and so that's the so-called thermosteric effect, which is here. There is a salinity change effect called the halosteric effect. You put them together, and you get the steric effect. And that's one way that you get sea level rise. Another way that you can get sea level rise is because currents actually change the surface of the earth, the surface of the ocean, and their eddies and other things. That's another part of sea level rise. The only point I wanted to show you this figure is to give you a starting idea that warming of the oceans leads to sea level rise. So there's also a hockey stick for sea level rise. And the hockey stick for sea level rise is that the global mean sea level rose faster since 1900 than in any century in the last 3,000 years. So similarly unprecedented change. So that's alarming. And you can go deeper into this, and you can break down what the constituents are, like which part of the energy in the Earth system is changing. So the energy's coming in, and then it's not going out because of greenhouse gases trapping it. Where did all that energy go? And like I just said, most of it's going into the ocean. It's going to the ocean in different depths, mostly at the top, but also in the mid-depths and a little bit at the bottom. And then some of it goes into melting ice, some of it goes into warming up the land. And this little tiny purple at the bottom is the warming of the atmosphere, which is the part that in some sense we're really worried about. But in energy metrics, it's not a lot of contribution. It's the leakage of the energy from the oceans that's warming the atmosphere, if you like. And then this is the same game, but doing it for the sea level budget. So the ocean expansion are these three, and then there are glaciers melting on land and dumping the water in, and then there's Greenland and Antarctica melting on land and dumping the water in. The land water storage is changing as well, which means that like ponds and lakes are emptying out into the ocean. You put all those together, and you get a sea level rise story. And then this dashed line at the top is what happens if you observe sea level rise from satellites, and it's, at least within error bars, consistent with the sum. So it says, we know the energy story and the sea level story is closely related to the same warming that's coming from the energy story, and it's closed. It means we're not missing any constituents. So we didn't add this up, and if we had added this up and then the constituents didn't add up to the total sea level rise, we'd be like, oh, the sea level's rising for another reason as well. It isn't. So you could say we should be measuring this more precisely, but that's a different question, which is not really possible. Okay. So if we like then, both the story of the global warming, in some sense, this energy budget, and the story of the sea level is getting energy into the ocean. So how does that happen? Well, there's air-sea exchanges of properties. There's wind blowing on the surface. There's fresh water raining on, and then evaporation coming out, which has an energy source, even though it doesn't take any salt with it. There's the heat flux that you might be worried about. So this is an estimate of the present day of all of those. This is the wind stress, heat flux, and freshwater flux. Here's what observations tell us. Here's what the models do over the same window. And you say, oh, well, great. I'm just going to go and let's see this guy and that guy. I could compare, and then I'd see how good the models are at the forcing part of this story. Right? If they're doing the same changes in wind stress over the last 20 years that the world is seeing, then they're doing a good job, right? And now we enter the world of the stippling. All the places that are stippled here are too noisy to make even a sign determination of whether the fluxes are getting stronger or weaker. All of the ones over here with the slash lines are saying that climate models are disagreeing in sign about whether it's getting stronger or weaker over the last 20 years. And now when you look back at these maps, you're like, there's not a whole lot of signal there that I believe. Like maybe this blue and that blue could be compared, this red and that red a little. But you get worried about whether we're actually monitoring changes to any of these fluxes effectively enough to constrain the climate model changes in fluxes. So the freshwater flux, we could not worry so much about the flux, the exchange, but we could just pay attention to how salinity around the world is changing. We may not be able to watch the flux, but of course the ocean is watching the flux all the time, and it accumulates flux anomalies as salinity anomalies. We just talked about the energy budget. That's the anomaly of this net heat flux. You put those together and you get the steric sea level rise anomaly. So then now we're actually monitoring some parts of this. What about the wind stress anomaly? This is where waves come into the game. Waves are watching the winds for us. They're being formed by winds always. They don't respond instantaneously to winds, but they respond to sustained winds. So we can go ask if the climate models that produce this very, very noisy wind trend and the real world that produces this very, very noisy observed wind trend give us waves that are doing consistent things between the real world and the modeled world. And so this is an example of that. This is the wave height of a climatology. So this is observed, essentially, significant wave height. This is the multi-model mean of the biases in modeled wave heights. And you can see that, there are differences, but this is only a 0.5 and this is a 5. So basically the bias in the climate models is small in terms of how well it's doing providing the winds to drive the waves. So this is a better tool, just like the energy budget was a better tool for measuring the air-sea heat flux, and the salinity budget was a better tool for measuring the air-sea freshwater flux. The waves are a better tool for measuring the air-sea winds because they accumulate an effect and kind of filter out the noise for you. And you can say, well, okay, do we really know? How good are these observations? Like, are we really constrained? And so this is multiple versions of this, essentially, the difference between them. And these numbers are also quite small. So it says that the multi-model error is detectable. It is larger than the inconsistency in our observed wave fields. And it is informing how well the winds are being simulated in the climate model in a way that we could try and get better at doing this. So it's now another tool which we could use. It's a new set of observations. We're observing waves, not just observing winds. We put that together, and we can actually use the waves to detect climate change, at least climate change in the oceans, and climate changes in the wind field. And the last piece of this story is, sea level. We're not actually going to see the mean sea level rise. That's not going to bother us very much. We're going to notice that long before it gets problematic. But what we will notice is that floods are going to happen more and more often. And so this is under very strong global warming and very weak global warming and mid-range. And all these little dots are the location of tide gauges around the world. which is just kind of a convenient way to visualize this. And then this is an amplification factor in the frequency. So down here at 1, if it's a white bubble, it means at the year 2050, it'll be just as likely to have a flood at that location as there is today. If on the other hand, it's this dark blue, it's 1,000 times as likely. So a 1 in 100 year event becomes a monthly event under this level of amplification. And the thing that should alarm you is the fact that almost all of the bullets up here are in this color range. So coastal flooding goes from things that are now once in a century scale devastating events to monthly events, which means that you basically have to just change where you live. You can't really accommodate 1 in 100 year floods monthly. And of course, that's just for the mean still water level. On top of that, the wave field is changing. And so when you get a flood event, you don't only get flooding, but you also get waves and winds, storm surge, other pieces that add to that. So the level of inundation could also change because the waves are changing and the winds are changing. And so this is a map just showing that actually in most of the populated world, actually the significant wave height is decreasing. So the waves are actually getting lower. So maybe the combined effect is a little better than you might have worried about. Down here, the waves are getting stronger. That's something to think about. Okay, so waves drive mixing. Waves can detect climate change and also play a little role in the sea level inundation question. What about this last piece? This part is a little tricky, and this is an example of a semi-novel technique of how you try and analyze things. So it's really the technique that I'd like to show. But here's the key question. Oops. What happened to my question slide? Oh no, my question slide has disappeared. I'll tell you what the question slide should have said. The question slide should have said, okay, you've told us a lot of really weird things about waves and how they interact with other things. Does it actually matter? Like, is the effect big enough? Like, when we get down to brass tacks, we get a little bit of extra vertical mixing because of waves. Does that account for anything? And I'll say, oh yeah, sure, it makes the boundary layer depth 10% deeper. And you're like, well, 10%, what is 10% interesting? Is 10% like enough to make climate different? Enough to drive changes in climate? So that's what I'd like to close on, is how we can estimate that. So we have that story of energy. And that energy is coming from the atmosphere into the ocean through the mixed layer, which in some sense is that little layer we were talking about getting mixed up by all those turbulent phenomena. But it's also the mediator of exchange of energy between the atmosphere and the deep ocean. It's the thing that's the first line of defense. When something tries to come into the ocean, it goes in the mixed layer, and then maybe it goes out back into the deeper ocean, or maybe it comes back into the atmosphere. The dynamics of the mixed layer have a lot to do with that. But it's also the home to Langmuir turbulence and submesoscales. So all those phenomena we were talking about before are going to have an impact on simulations of the mixed layer, or in the real world, those phenomena are part of what's setting the properties of that mixed layer as it evolves season by season here. So this is going around and around. These are observations. The only thing really to notice is that in the wintertime hemisphere, it's deeper. And in the summertime hemisphere, it's less shallower. It's kind of shallow around the equator everywhere. And the range of scales is, it could be 10 meters deep, kind of in the tropics, up to 1,000 meters deep in the deep winter time in the really cold places. That makes sense to everybody? There are, this is not a pure float-based measurement, but there are 4,000 floats that have been measuring continually, all of them taking a measurement a week roughly since 2005. And then that synthesis of those, I think it's around 4 million independent profiles, and each profile has maybe 100, 200 observations in it, is what goes into this data set. So it's a lot. But it's actually not very good sampling because the Earth is really big. So it's kind of a lot of observations, which is not enough to do this problem as well as you'd want. And this is what it looks like from the side. We have this mixed layer that in different seasons is getting deeper, and then it's getting shallower in the summertime and deeper in the wintertime. And these are actually observations at the particular place called Ocean Climate Station Papa, which is a little mooring. But this is really important for predicting weather coming into the Northwest and Alaska. So before they had this mooring, they actually used to park a boat there all the time just to take weather observations, which is like, that's kind of cool, whatever. So this is a very long, at this one location, there's been a very long time series. So you can watch this annual cycle come and go. We understand this part of the world very well because it was helpful for weather forecasts. So it's mixing, and it's being heated and cooled at the surface. And so the mixing is making it deeper, and maybe the cooling is making it deeper. And then in the summertime, it's warming up and kind of recovering as it re-stratifies. So it's temperature, but it's also depth that's evolving. So if you want to do a little order of magnitude budgeting, global warming is about 0.7 watts per meter squared of power. That would warm, if it just went to the atmosphere, it would warm the atmosphere about 1.5 degrees every year, which is good that there is an ocean to make that not happen. The atmosphere has the same heat capacity as about the upper 3.4 meters of the ocean. So if you just had if this was only 3.4 meters deep, it would also warm that fast, but it's actually maybe closer to 34 meters deep. So it's 10 times smaller. So that's about 0.15 Kelvin per year. This thing is jumping back and forth by a whole lot more than 0.15 Kelvin per year. This is maybe about 1% of the mixed layer seasonality. So now therein lies the problem with global warming simulations. Signal, noise. Like it's a tiny change to a very dynamic system. That's why those air-sea fluxes were so noisy. That's why modeling it is hard. And so when we go and I say, this is basically showing you, already said in words, when you add the Langmuir piece in, you get about 10% deeper. That's interesting. It's a perturbation. It's bigger than that global warming signal. It's important, but that doesn't quite get to where we want to go. And this just says we reduce bias in the modeling if we do that, which I'm not going to, except for the cool animation, I'm not going to dwell on. And if you include these kind of things, they also affect that boundary layer depth by about the same 10% or so, maybe in the opposite direction. Different forcing drives one versus the other. Oh, so here's the question slide. Let's get real. Let's see if we can estimate how much that matters. And we're going to use a trick of something called an emulator. So this is the Nobel Prize winning physics, Hasselmann's model, which basically says if a random atmosphere forces a mixed layer, you get a temperature response, and you might restore it back to some climatological value. This is a simple stochastic model. And the only important thing here is that because the ocean has a higher heat capacity, it responds more slowly, and so you get kind of a red spectrum response. So the ocean is filtering out all the high frequency stuff from the atmosphere. That's one little toy model. A different toy model is like kind of how the ocean works globally. There's sinking Gulf Stream sinks down and becomes North Atlantic deep water in the North Atlantic, and then there's a complicated thing that happens in the Southern Ocean. It's kind of light water on top of dense water. This is a different way of thinking of things, but this is also kind of a simple toy model. And then there's a funny toy model in between, which is just this set of differential equations. There's two ODEs. This is one surface temperature and one deep temperature. And they're evolving in response to forcing, just like the Hasselmann model did, of forcing from the atmosphere and maybe a restoring term. And then they're allowed to exchange energy one to the other. And these are just, one temperature describes the whole world. One temperature describes the whole deep ocean. Nothing complicated about these. Amazingly, these two equations can be fit to a climate model and do a pretty decent job of matching the surface temperature evolution, this guy, from a climate model with just the parameters in that model. And so cool, you can make a climate model much faster and experiment with like different forcing by doing that. Cool. That's what makes it an emulator. It emulates a climate model. It's cheap. It's fast. Unfortunately, none of these parameters are observable, directly observable. So you need to relate them to something else before you can estimate how important they are, how they might change. And that's where the story comes in with the mixed layer depth. So we can take mixed layer depth from those same climate models and connect them to the parameters of this model. And they do have a kind of relationship. And then we could correct them back to the observed range of mixed layer depths. And so this vertical bar is showing you where observed mixed layer depths are. in those 3 regions, this one, and this one. And by that process, we could estimate what would happen if we could fix the mixed layer depth to be just the right value, just the observed value with all those crazy floats. And we could use this emulator then to say, how does that change the climate? If we could make the model have the right mixed layer depth, what does it do? And this is what it does. So this is now zooming out. This is 2 different experiments, a kind of impulse increase in CO2 versus a slow increase in CO2. And the outer envelope is what all the climate models do. And the inner envelope is what the climate models do if you constrain them to have the right mixed layer depth. So there's a 20% reduction at this transient phase and about a 45% reduction in the spread at this long-term range. And I'll leave this to you to take a look at. If you can reduce this number by 50% in time to do things by 2020, which you already missed, it's worth $10.3 trillion. If you can reduce it by 2030, 9.7 trillion. That's not chump change. This may not be the solution to that problem, but this problem is so valuable that even a partial improvement and understanding toward this direction is worth doing. So that's what I wanted to say. Thanks, everybody. Sorry to run a little over.
There have been a few questions, but I think we have time here for a couple questions for Baylor. Are there any? Yes, please.
You showed us a lot of simulations. For all the physics you're looking at, there's a huge separation in time scales and length scales. So are you dealing with models that freeze out the unimportant scales, or do you have sophisticated numerical methods to deal with these stiff problems?
So
Could you repeat the question?
yes, I can repeat the question. So basically the question is